Hi there, welcome to justAnotherDev, and today we are going to discuss about linked list in JavaScript. So linked list is basically a linear data structure which links all the separated elements by a reference field, and it is very similar to an array data structure. The only difference is instead of referencing the elements using the index, the elements in the linked list are connected by a reference. Basically, reference can be of two types. It can be a forward reference, or it can be a forward and back reference, which is basically called singly linked list and doubly linked list. Also, it provides efficient insertion and deletion operations compared to an array. Let's see how. So as we discussed, in a linked list, the elements hold reference to the next element. So if you can see here, this one element or the linked list node is having a reference to the next node, which is 2, and so on and so forth. The references are created, and the end element does not hold any reference. Basically, it has a reference to the null element. So assuming if you want to delete a node over here, right? So let's say if you want to delete this node 3, then what will happen? We just need to delete a reference and we don't need to do anything, right? So we will have to create a reference from here to here, and that's all. So this reference will be deleted, and we will have a reference from 1, 2, 4 and 5. So that's how we can basically delete an element in linked list. Now let's see how we can update an element, or how we can insert an element inside a linked list. So let me just create it again. Now in case we want to add 6 after this 3, then what we can do, we will create a new reference which is going to point to this 6 by deleting this one, right? So we will delete this reference, we'll add this reference from 3 to this new node 6, and the reference from 6 will basically point to this 4. So that's how you can basically insert an element in a linked list without changing the structure of the, or basically without changing any other element in the linked list. You don't have to touch any of the other elements. It's just that you can simply delete or insert an element by only changing one reference. Some of the real life examples of linked list is basically a playlist. So if you've seen music players or the music player applications that we have in our phones, so we have a playlist, and inside the playlist you can see options like, okay, move the song up or remove the song from the playlist, or there are features like, okay, play next, right? So you can select any song and you can say, okay, I want to play it after this. So all these things happen by managing this playlist as a linked list, right? Because there are so many frequent updates or there are so many frequent insertions and deletions that can happen in a playlist that is present in a music application. So that's how you can maintain a playlist as a linked list. So in order to create a linked list, the first thing that we would need is the list node, or basically the element that we are going to create in linked list, right? So what does a linked list node contain, right? So a linked list node will contain a value which can be anything, whatever value we are providing, let's say number 4, and then it will contain the reference to the next node. Let's say by default we are setting it as null. So this next node will be pointing to another node object when there is a new node coming into picture, but otherwise by default we can set it as null, right? Now let's come to the linked list part. So the first thing that we should be able to do is initialize a linked list, which will basically create a head item for us. Now this head item will basically point to the very first item in the linked list, right? Very first element or node in the linked list, right? Also it will have a size. Size will basically tell us how many items are currently present in the linked list, and it will keep on changing as and when we add or remove items from the linked list. The other thing we want is to insert or add, let's say, at a particular index, and maybe at beginning and at end. also delete at a particular index, or maybe at beginning or at end, right? And then finally we can have one more, like get the value of node at a particular index. So these are basically the functions that we would need in our linked list. Now let's see how we can implement it. So the first thing that we are going to create is basically creating a list node. So I'll just create a folder over here. We'll call it linked list. We create a folder. I'll move this over here so that we can have the required files over here itself. Let's just call it list node.js. Now in this list node, we are going to create a constructor function called list node, which is going to provide us a node for our linked list, and we are going to set the value for this node as whatever we are going to send it in this constructor function. And by default, let's say this list node is pointing to a null pointer, a null reference. So this is basically our list node. I'll just export it. Okay, coming back to our linked list. So what we are going to do, we are going to create a constructor function over here as well, which is going to create a linked list for us. And initially we will have a head which can point to null, or we can create a dummy node as well, which is also called a sentinel node. So the reason why it is a good idea to create a dummy node or a sentinel node is because you don't have to check if the head is present or not, the head value is null or not. So you can always create a list node which is going to be your head or sentinel node or dummy node, and it will always going to point to a null value initially, right? So let's keep the size as well of this linked list to be 0, because this is a dummy node. This we will not keep in account for the size calculation, right? Now this is basically how you can initialize the linked list. Now let's write our other functions, basically how we are going to add a node to a particular index. So what we are going to do, we are going to create some functions on the prototype of this particular constructor. So I'm going to write linked list dot prototype dot add at index, and this is basically a function which is going to accept the index and the value. Now what we need to check here is basically we'll have to verify if the index is within the bounds or not. So if the index is less than 0 or index is greater than the size of our linked list size, then we can just return null. We are not going to do anything. But if the index is valid, then what we are going to do, we are going to create a pre node. Let's call it pre, which is going to point to our head. Basically we just added a variable which is pointing to the head or the sentinel node that we created. Now in order to add at a particular index, we'll have to be before that particular index, right? So for example, if the nodes are like this, 1, then 2, then 3, something like this, and let's say this is our sentinel node which is pointing to this 1, 2, 3. So if we want to add, and our indexes start from here 0, 1, 2, right? Because sentinel node we do not consider for our actual elements. So if you want to add at index 1, what we will have to do, we will have to move this pre node which is pointing to this to 2 steps, right? Sorry, 1 step before that particular node. So if you want to add something over here at index 1, then what we'll have to do, we'll have to come over here, we'll have to add one more element. Basically what we'll do, we'll break this chain, we'll add let's say 5 over here. So 1 will point to 5 and 5 will point to 2. So this is what we need to do, right? So what we are going to do, we are going to reach to that particular index, say I equals to 0, while I is smaller than index. The reason being, we need to reach to the first index, right? We need to reach to the element which is before the index that we want to add a new node at, right? So if we wanted to add a new node at position at index this, so we reached at 1, we added a node here, and then we created these references properly. So what we are going to do, we are going to keep moving our pointer as pre equals to pre.next, and then we are going to increment this iterator as well, the I equals to 0 variable as well, right? Now we have reached at the position after which we need to add the particular node. So what we can do, we can hold the reference, we can keep the reference that we are going to delete. So let's say current reference equals to pre.next. Basically what we did, initially it was, I'll just put it again, initially it was like this. 1 is pointing to 2, 2 is pointing to 3. Now since we have to add 5 after this, so we'll still have to keep this reference, right? This node reference should still be there. So that as of now 1 is pointing to 2. So what we are doing, we are keeping this current reference. Now this pre, which is pointing to this 1 over here, we are saying pre.next equals to new list node, and the value that we wanted, basically we are going to get the value from function. So this node is created. Basically what we have done, we have established this link 1 to 5, but this 5 should also point to this 2 now, right? So what will happen, let me just call it a new node. So pre.next will point to this new node, and this new node dot next should basically be pointing to our current reference. So now what we have done, we broke this link, we established this one, and we created a link from this to this because we hold this reference for 2 in our current ref variable. So this is how we are going to add a node at particular index. Also we have to increase the size by 1, right? Same thing will happen for dot add start, let's say. So added start is nothing but added index 0, right? So we can just create this function and return. So if you want to add any value to the beginning, what you can do, return this dot add at index, the index will be 0, you can pass the value. Similarly what we can do for the end, we can just put the value as size over here and return it. Now let's see how we can, sorry, it should be linked list, not list node, because this is a function on linked list. Again, linked list dot prototype dot delete at index. Now here also we want to delete an item at a particular index, right? So let's say in this one we want to delete this 5. So what we'll have to do, the index for 5 is 1, so we'll have to reach till index 0, then break this relation, right? So this point, this pointer, this next should point to 2 directly and not 5. So let's see how we can do that. Here we'll have the index. Again we'll be using something similar. We'll have to check for the index if it is inbound or not. Okay, so till here it is all fine. We created a pre node which is pointing to the head. We will try to reach the index before we want to do this delete operation. Here in this case, let's see if we want to remove this 5, we have reached till 1, and now what we have to do, this pre is pointing to this 1, so what will happen, pre.next equals to pre.next dot next. So this is basically what we'll have to do. Okay, so what we have done here, this 1.next is going to point to what, pre.next.next basically means pre.next is 5, and this dot next is 2. So we are saying this pre dot next should point to this one. So 1 will point to 2 now, and this is basically how we are removing this reference of 5. Also, after removing this, we'll have to reduce the size by 1. So this is how we can delete a node at a particular index in a linked list. And now let's see how we can access the value of a particular node at an index in linked list. So get node at index equals to function, and here we are going to accept the index. The code remains mostly similar. The only difference we'll have here is that now that we want to get the value of the particular node at a particular index, so let's say if we want to see the node at index 1, so what we'll have to do, we'll have to jump from this sentinel node to this node and then to this node. Now we are not relying on the previous node, instead we'll have to go to the node that is basically concerned. So here we'll change it from smaller than to smaller than equals to, and then we are going to return pre dot value. So what we have done over here, we are pointing to our sentinel node, and then we are moving it to the index that we want, and then we are finally returning the pre dot value. So let's see if this works fine. So I'll create one more file over here called testll.js, and let's create a linked list. Okay, let's add some data into this. Add at index 0. Let's say I'm adding 15, then I'm adding 10, I'm adding 5. So it will essentially become something like our sentinel node, or basically our head node, then 5, then 10, then 15, because we are adding at index 0 every time, right? So initially it was the first value, then it became the first value, and then this one became the first value. So the order became 5, 10, 15. Let's see if we are able to see if it is working. So if I do a console.log ll.head, I'll just do a json.stringify so that we can read the object properly, and I'll just do node linked list testll.js. So if you can see, we have the sentinel node first 0, followed by 5, then 10, then 15. Let's see how we can get the value of a particular node at index let's say 2. Get node at index, and I am putting 2 over here, so it basically should return 0, 1, 2, that is 15. Let's see if it is working fine. Yes, it is returning us the value 15. Now let me remove some value. Let's say we want to remove this 10, and what we are going to do, we are going to print it again. Just clear this up and run it again. Okay, so we can see it was 5, 10, 15, then now it is 5 and 15. So we have removed this 10. So this is basically how our linked list is implemented in JavaScript. Now let's look at the time complexity of these operations. The time complexity of operations like insert, delete, and get turn out to be O of L in linked list, where L is the index where we are going to perform these operations. So for example, if you want to perform this operation at index 0, 1, 2, then you will have to traverse from here to here, and then only you can perform these operations. So in the worst case, the time complexity becomes O of n, because you might have to traverse through all the linked list nodes and then only perform these operations. But the average case time complexity still remains to be O of L, which is better than the array, and particularly the arrays in other languages like Java, C++, where arrays are stored in a contiguous memory location, and you cannot directly insert or delete array items at any particular index, right? Because it will have to create the whole array again and then give it a new memory location. Therefore, linked list becomes better choice over arrays when we have a lot of insertion and deletions. So that's about the time complexity of linked list. Thanks for watching and stay tuned.